seminar series of this year. And it's really our pleasure to have with us Professor Petar Popovsky, who is a professor at Aalborg University in Denmark. And he is really well known for his work on wireless networks. And today will be telling us about 5G. He received his PhD in 2005 from Aalborg University and is a fellow of the IEEE, has received a number of prizes. I'll mention just a couple of them here: the IEEE Ellersick Prize and the IEEE Rice Prize. And he's also a member at large of the Board of Governors for the IEEE Communication Society. He's the author of a book called Wireless Connectivity, an Intuitive and Fundamental Guide. And really, we're excited to have him here and look forward to hearing your talk. Thank you for joining us.
Thank you very much for the kind introduction, Bhaskar. And thank you, Bhaskar and Pierluigi, for inviting me. It's really a pleasure to give a lecture at this seminar. So I'm going to share my screen. I hope you can see it. Let me see.
Yet.
Let me see. It worked well. Don't worry, it's coming.
Yeah.
Excellent. So, as it was mentioned, the title of my talk is Wireless Connectivity Beyond 5G. I'm going to speak a little bit about spectrum, or about what is time and timing in wireless system, space, features, and something about distributed ledgers and blockchain. So this is the outline of my talk. I'm going to start from the bottom with connectivity types. Then I'm going to go to spectrum slicing. Then I'm going to speak about connectivity and timing and connectivity and space to, let's say, to different developments with respect to the connectivity area. And then finally, I will end up with the distributed ledgers and their impact on IoT traffic and why they're important for the upcoming IoT applications. So let's start with connectivity types. So the connectivity ecosystem is actually quite complex because it grew through the generations, not only of 1G, 2G, and the others, but also Wi-Fi and other connectivity technologies. It grew to a very complex set of connections where we have people-to-people connection, machine-to-machine, people-to-machine, mixed satellite, car-to-car connections, and so on. And so these are all connections which have different coverage, different duration, different data rate requirements, reliability, and so on. So the way 5G decided to deal with this complexity was to segment it, to simplify it. So the main thought in 5G is that there should be three generic services. One is called enhanced mobile broadband, one is called massive machine type communication, and one is called ultra reliable low latency communication. And if the thought behind 5G was that if we are able to support each of these services, then we are going to basically support any type of connectivity that can come in the future. So in my opinion, the most original idea of 5G is that it has a platform approach to support flexibly heterogeneous services. So it can actually adapt to all these different requirements. So these requirements, they can be specified in details, but for the purpose of, let's say, modeling in communication theory and for the purpose of understanding the essence of this, we can actually simplify them to the following. Enhanced mobile broadband can be understood as an acceleration of 4G, where we have large payloads like in video transmission or any multimedia transmission activity over long periods, for example, like streaming of video. And then we want to maximize rate, but the reliability per transmission per packet is moderate, for example, 10 to the minus 3 packet error rate. Then we have massive machine type communication, which is basically the traditional IoT of simple devices where we have a fixed low rate but unknown active subset of massive device set. So for example, we have 10,000 sensors connected to a base station, and we don't know actually which subset is active at a given time. So what we would like to maximize here is not the rate not the data rate per sensor, but we would like to maximize the arrival rate, so the activation rate of these unknown subsets. And the reliability per one IoT device may not be high, for example, 10 to the minus 1, if we take, for example, a smart meter. But from a population or over a certain time interval of transmission, then we would like to have a high reliability. For example, there is a smart metering company which says that within a couple of hours, at least one packet needs to be received from its smart meter, but individual packets are not important per se. And finally, we have the ultra-reliable low latency, where we speak about intermittent transmissions, but from a much smaller set of devices, like robots communicating within a factory floor, or cars that are trying to reach a consensus, self-driving cars, and so on. So here we want to have very high reliability, but the transmissions are localized in time. And the way we should think about these connectivity services is that these three types of generic services are kind of some eigenvectors in certain connectivity space, and any future service will be built by combining them. For example, if we have a factory, we can have a tactile interaction with the robots, which requires this ultra-reliable low latency. But from time to time, there is a transmission of a video from certain parts of the factory, or there is a rendering of a picture, of an image in augmented reality scenario, and that would be broadband. And then we also have, for example, sensors from around the factory that are providing information which is fused and then combined with the other connectivity types. So what I'm trying to say here is that the role of communication engineers here is to provide these generic services, and probably some other creative people that are going to build applications are going to use these three types of services. But it's also fair to ask, is this the ultimate connectivity framework? So the point is that these three services were not defined through certain optimization process and certain formal model. It's just pretty heuristic. So it's actually very difficult to say if this is the ultimate connectivity framework, because as von Neumann said, we should not make predictions for what can be achieved with computer technology in a period which is longer than 5 years, because it might turn out to be silly. And I think this is still valid today. And these two other fellows with him are Richard Feynman and Stanislav Ulam, which are all three of them are very well known. What the new service, I would say, of these three generic services is the ultra-reliable low latency, and the 5G community has opted to couple ultra-reliability and low latency into what is called ultra-reliable low latency communication. And for a long time, the requirement has been to have a packet error rate of 10 to the minus 5 under the proverbial 1 millisecond. There are a lot of problems with this statement. First of all, this is statistically not correct statement, because this assumes that there is certain distribution that you know of, and then you can calculate with respect to the distribution tail of 10 to the minus 5. Actually, this distribution is not known, so it has to be learned, and so on. So there's a lot of, we can have a separate lecture for that, but for the moment, I'm saying that this statement is statistically not very justified. On the other hand, if we go to information theory, in essence, information theory guarantees perfect reliability. So the error rate which tend to 0 under two details, basically. First is that the sender knows the channel statistics, and it's capable to select the data rate, capable to find codes which are operating at data rate, and then transmit just below the channel capacity. If this happens, then we can achieve, in principle, perfectly reliable communication, with the second condition that we can allow infinite latency. Of course, infinite latency is not practical, so we are actually always looking for latency constraint. The question is, should it be 1 millisecond or should it be larger? So when in the early days of 5G, like 8 years ago, we were defining two types of ultra-reliable connectivity. One was over long term with latency more than 10 milliseconds, and the other was over short term, latency below 10 milliseconds. 10 milliseconds was chosen based on interviews with the different stakeholders. And this is not a magical number. It's not been proven that this is the number, but I can see that in the latest 5G requirements pulled by 3GPP, there is also this segmentation with respect to latency. So there is not strictly looking for 1 millisecond, but there is more awareness that there could be more latency relaxed applications that still require high reliability. So example of these connections are, for example, mobile health and remote monitoring, disaster and rescue, and smart grid. For example, the smart grid in Europe, the grid runs on 50 hertz. So that means that any important event happens within 20 milliseconds. So that could be the latency target and the multiple of this 20 millisecond. And also, if you look, this report from the 5G Association for Industrial Connectivity, you can see that they are defining actually 3 types of connectivity. One is non-real time, the other is soft real time, and the third one is hard real time. So based on this, I think we can kind of revise the connectivity space by putting 4 dimensions, having data rate, reliability, latency, and massiveness. And then tactile robotics is still requiring high reliability and low latency. So this is kind of URLLC. Data rate is not very high, massiveness is not very high. But then health monitors, they require very high reliability. There can be a massive number of them, but latency and data rate are not significant. And then we can have augmented reality where data rate and latency are dominant requirements. And then this is kind of trying to map the space of connectivity. But in my opinion, the important challenge that we're going to face in the coming years is the need to improve, to have improved understanding of this connection ecosystem and how these different types of traffics are interacting. For example, how can we characterize statistically composite connections when we have broadband traffic, which is intermittently intercepted by ultra-reliable low latency traffic or gathering of data from massive set of devices and so on. So for example, if we have virtual reality setup or augmented reality, then we know that a certain tactile request might lead to a high data rate requirement. So modeling these statistical dependencies between the traffic is very important to achieve very efficient use of communication resources. Another thing is that when we define this massive machine type communication and ultra reliable low latency, then there was also a talk, why don't we have simultaneously massive and ultra reliable? So this is in a sense paradoxical, because if you can have ultra reliable low latency for massive number of devices, then it should be very easy to do it for low number of devices. So there's a catch in this, right? And the catch is that in principle, we can have jointly massive machine type communication and ultra reliable low latency, provided that the information across the devices is correlated. And we have actually tried to show this through a very simple model of a IoT system where the devices are reporting their own status, but from time to time, they detect the same alarm, the same physical phenomenon, and they're sending the same information about that alarm. So in principle, the set of sensors operates like a IoT, like IoTs that are different sources of information, but from time to time, they're trying to transmit the same information. In that case, they act as multiple antennas of the same system. So this is yet another example of correlation of traffic. And I think we are going to see much more of this once we start to understand the requirements of cyber physical systems. For example, robotic systems, interaction of robots, interaction among humans and with human in the loop, humans and robots, and which kind of traffic requirements and traffic patterns they will lead to. So let's tightly related to this is the issue of spectrum slicing. So what I mean by spectrum slicing here, if you look into the, for us in Europe, it was an important call for project by the EU Commission for smart connectivity beyond 5G. The first sentence was provision of seemingly infinite network capacity, including innovative spectrum use and management. So I guess the projects that promised to have infinite network capacity didn't pass because we know it's possible, but still indicative that we are going for a very good use of spectrum and a very efficient use of spectrum. But based on what I presented before, some of you might ask, how do we measure the spectrum capacity or spectrum efficiency when we have, let's say, 2 users where one wants to have a very high rate and another wants a fixed rate, but low latency and high reliability. So basically for the second user, we do not care to maximize the rate. So we should not measure the spectrum usage by bits per second per hertz, but we care that we satisfy the requirements of that user. So how do we measure the spectrum when we have this heterogeneity? And well, this is what I call spectrum slicing. It's coming from the area of network slicing, which is basically offering differentiated services, different guarantees to different types of connections. For example, some that want latency, some that want rate, and so on. And what we are saying is that you can bring the same philosophy of guaranteeing heterogeneous requirements to different services, but just in the spectrum part. And the spectrum is a different thing compared to the usual computing resource or communication resource in a wired network, because spectrum is shared. So it's not obvious that we just have to allocate different spectrum to each of these different types of services. And then if we take the three generic 5G services, eMBB, URLLC, and mMTC, and if we take this, for example, uplink scenario, we can build a communication theoretic model that tries to understand what are the trade-offs in using the spectrum. And the way we are going to assess spectrum for these types of services that I have talked so far is not in terms of data rate, but we're going to evaluate in terms of trade-off. For example, if machine type devices are sharing the spectrum with a high rate device, then we want to see how the data rate of the high rate device is decreasing as the activity of the IoT device is increasing. So that's the interesting type of question that we want to answer with respect to these 5G and post 5G services. And there are two principal types of slicing. One is orthogonal, where we just allocate, is the obvious one, where we allocate separate resources to separate service. The other one is non-orthogonal, where we actually allow the services to interfere, but we use advanced techniques in order to extract the desired signal and guarantee performance to these services. So let me give you a toy example of this instead of going to the complex communication theoretic model. So this example is with two users. One has broadband connectivity, continuous transmission, example of a video stream, and there's a target of getting a high data rate. And here we have a low latency user, this guy who has intermittent transmissions, example is a reliable control, and the target is latency and reliability. So both of them are transmitting to the common base station in the uplink. This example is taken from this book, which was mentioned by Bhaskar, which I've written recently. And let's take the orthogonal slicing. So this is, as I said, this is a toy example, just taking a single communication channel, not multiple frequencies. And then we say, okay, let's allocate orthogonal resources. So we take a period 4 in this specific example. We allocate 3 slots to the broadband user, and we allocate 1 slot, every 4th slot is allocated to the low latency user. So obviously here, the low latency user cannot get latency which is below, which actually cannot be 1 for each transmitted packet, because there could be packets that should wait 4 or 5 slots even, right? So basically here, the broadband user is not affected by the activity of the intermittent user, and the intermittent user is limited by the orthogonally allocated resources. So we can say that the broadband goodput is fixed, and then there's no interaction between these services. Now let's take an alternative slicing. Let's take a non-orthogonal one. So here, in the previous one, they were not affecting each other. So here we say that the broadband user takes a packet and repeats it 3 times. And the intermittent user is allowed to transmit the packet whenever it arrives. So that was not the case before. So look at this first packet transmission here. The base station, which I call basal, receives a collision between these 2 packets, but actually the base station has already decoded this previous packet, so it can use it to cancel this packet Z1 and decode Y1. So in principle, what we are showing here is that we can use advanced successive interference cancellation. We can sacrifice the rate of the broadband user, and then by that we are actually allowing a lower latency for the intermittent user. And we're currently working on more advanced models of this, but this is I would say very illustrative model to tell what are the basic trade-offs. So how you can actually sacrifice parts of the performance of one of the users in order to get performance of the other type of user. So in general, we can say that spectrum regulation is something which is changing over a long time. So we can see a spectrum regulation as some form of axiom for building wireless system. And based on these axioms, we are building the system. And then in the case of 5G, we actually introduce new models for new types of connectivity. And then we are trying to understand the new trade-offs which are arising from heterogeneity, just like in the previous slides. And hopefully, over a longer time, this is going to lead to new types of spectrum allocations, where we are going to have methods for sharing the spectrum or slicing the spectrum, as I called it, to guarantee different types of performance to different users. Let's move to the timing question. So as I said, latency plays a key role in 5G. So if you read even popular articles about 5G, they speak about this low response time, low latency, and so on. So a good abstract way, in general, a quite general way to represent latency and reliability in a system is to take on the x-axis the time, and the y-axis the probability that the packet of a fixed data size will arrive by that time. And of course, this probability is non-decreasing. So by time, the probability tends towards 1, but it maybe will never reach 1 because we can allow for the system to have errors from which it cannot recover, right? So it might happen that the packet is not delivered simply because, let's say, the user walks out of the coverage region. So this is a latency reliability characterization of a system. And then if we want high reliability, low latency, we want to move from the blue to the red curve. And the way we're moving from the one to the other is by adding some form of diversity. For example, we can add diversity in time in terms of coding, which should be done with care because of the low latency. We can add more bandwidth and add diversity in terms of frequency, more antennas. I'm going to talk about that a bit later, or even multiple interfaces, because in principle, your mobile phone has at least 5, 6 different interfaces, and you can take the packet, transmit, replicate it through different interfaces, and in this way achieve actually a high reliability and low latency, because in the simplest case, you will just decode the packet which comes from the first, the packet that first comes from through some interface. So how is this changing the design targets? Well, traditionally, we are looking into throughput. So basically, we want to move from the blue to the red line, and we are looking into the average value. So we want to decrease the average latency for transmitting a given data packet. And this is increasing the throughput, right? On the other hand, in ultra reliable low latency, we want to move from blue curve to the red curve and hit a certain latency reliability point that is required for operation of certain, let's say, cyber physical system. And then you might say, these two are actually identical. They're not, because there is a possibility to arrive to this latency reliability point with the green line. And this green line is actually very important in communication theory, because the basic philosophy of information, of channel coding in information theory is that you should not transmit data sequentially, but actually you should group the data into blocks and code it and transmit it. So in principle, after you have a code of certain size, you introduce extra latency, but then you increase the probability that this packet will be decoded. So let's look into the trade-offs in a very simple communication theoretic model. What are the trade-offs in a single transmission? So no, because usually we say if we have to transmit a small packet, then if we have a low latency, then basically the packet that we are transmitting has a very few symbols. That's actually not necessarily correct. So let's look into it. We can fix the latency to t. We can fix the data size to d, and then the minimal required rate is in terms of bit per second is d divided by t. Then we can actually fix the bandwidth. And this is giving, by Nyquist sampling, this is giving 2 BT channel uses or 2 BT symbols, which means that this data, if it's spread across all these symbols, is going to be the data rate per symbol or per channel use is RBPS divided by 2B. So obviously, if we are increasing the bandwidth, we are having more symbols. And if we have more symbols, the requirement for data rate per symbol is decreasing. So in simple words, instead of loading them with 16 QRM, if we increase the bandwidth, we can load them with BPSK, which is more robust. And then we can also fix the energy spent in time t, which could be basically the transmission power, the receiver algorithm, and so on, the number of antennas we are using at the receiver. And if we fix all these 4 things, then there is a basic finite block length information theory, which tells us what is the maximum reliability that we can obtain. But in principle, you can fix any 4 of these and then try to find the 5th parameter. So in high reliability, low latency, you fix the first, the t, and the last 1 minus epsilon, and then you can play with the other 3 to see what can be achieved in a given system. So, but latency is not the only thing which is required in this communication system. There are actually other types of timing requirements. There could be time interval between updates. Then it could be the freshness, how fresh is the information that has been updated. If the fresher information comes, maybe we can just purge the older information and represent the new one, and so on. So recently, in the communication theoretic community, there was increased awareness that latency is not the only timing measure that matters, but there is also something which is called age of information. So age of information or freshness of information is a timing requirement which comes from tracking applications like or other cyber physical systems, basically where we have sense, compute, actuate cycles that are not sensitive to packet delay, but are sensitive to the freshness of information. So here we have an example of a freshness update based on tracking of airlines, satellite-based tracking of airplanes. And age of information, and there are several byproducts of it, are better metrics to capture the freshness of information. So the thing in age of information is, if you can see here, we have arrival of an event, let's say of an update. Think of a machine that wants to send an update, and then this update is aging, and then at this moment arrives at the receiver. So that means that the age of the information at the receiver about this process falls to be equal to this one. So basically this is equal to this. And then there is another update and so on. So in this, so in principle, here we can ask the question, what is the optimal way to schedule, and even what is the optimal way to sample the status of a cyber physical system in order to minimize the age. Another measure is what is called peak age of information. Peak age of information is what is the most outdated information that you can have about the status of the system just at the moment when a new update arrives. And actually it has been shown that this could be related to the stability of some network control systems. And recently we have we have analyzed this actually in an edge computing scenario where we have an IoT sensor, where we have a one queue for transmission queue of the IoT sensor, and then we have a base edge server, a base station, which is receiving the data, and then there's certain edge computing, so certain computing task done over that data. And here we have a tandem queue, and this tandem queue starts to be very peculiar with respect to age of information because there's an interaction of a lot of quantities. And we have actually analyzed this for two cases. One was MM1 and MD1 tandem queue. So D here stands for deterministic processing time in edge computing. And the other was MM1 tandem queue, which is supposed to model the case of, let's say, satellite links, which are two independent satellite links. So the first M is for the uplink and the second M is for the downlink. So the point is that this is a new timing requirement and leads to new types of trade-offs. But the interesting thing is how the final, let's say, cyber physical system or some control system is going to be affected by the performance of this measure. There are other types of age of information. There's an interesting measure that came out last year from the from this group of researchers, which says that we should actually not penalize the age if the information at the source has not changed. So in principle, even if the information about the source is old, but it has not changed, so there's no problem in that. We only penalize the age when information at the source changes. And of course, this is a strong assumption because we need to be sure that we know, we are informed when the source is changed, and we can actually accurately evaluate the penalty, the function with respect to this change. And the most recent work, which was just actually yesterday accepted at the ICC 2021, is by my group, where we turn the things upside down. So we say that the common communication models are push-based. So the transmitter always has a good judgment what the receiver needs and a good judgment when to send it. But here we turn the things around. We have pull-based communication. And the motivation was, let's say that we have reading process that is different from the process where the transmitter is knowing everything about the needs of the receiver. So this is the case of, for example, of satellites. When we have a satellite pass, so only when the satellite is in the passing above the device, then we know that we can collect the information. Then it's also cloud-based queries to edge devices. We know that the edge devices should just provide update when they're asked. They should not constantly provide update. So in the database literature, this is called permanent subscription. This way in which traditionally age of information is measured is called permanent subscription. So we are measuring the age at any time. But here we have changed the model. And of course, this is leading to an interesting optimization problem because now we should not optimize the age of information at all times. We should just make sure that the age of the information at the query time is low. And now we are exploring this further with the possible use of predictive techniques for basically sampling the data in an edge computing scenario. So final remarks on the timing part is that latency, age, peak age, and so on are only instances of a class of time-related criteria that are related to certain mission fulfillment of the system. And let's say if we have a network control system, that mission could be certain level of stability of the system. Another popular criterion is consecutive errors or watchdog. So basically, if we have a production process and we have 3 or 4 errors in sequence, then the whole process stops. So this is the classical way in which we want to ensure high reliability of the connection and high safety, actually, of the whole system. The thing is that there is always a trade-off between good architecture, which is layering, and flexible timing requirements. So I think this ambition with this 1 millisecond of latency in 5G was that to say if we have a 5G providing 1 millisecond of latency, then any timing requirement of any application on top of it will be satisfied. But we see that this is a strict layering paradigm, which is fine, architecturally fine, but it might be very difficult to achieve in all possible scenarios. That's why we need to generalize the notion of timing, as I believe I have convinced you with some of the examples in the previous slides. Let's go to the connectivity and space. So there is a lot of development in terms of spatial processing in wireless systems. So one of the biggest innovation from the last decade is massive MIMO, which then morphed into what is called large intelligent surfaces. So these are surfaces which are with an enormous amount of antennas, and they are deployed on buildings, on the walls, and so on. And the latest trend here are the reconfigurable intelligent surfaces. So basically the surfaces which are put in the environment, and they are capable to affect the propagation of the wireless signals in order to achieve certain goal, which is in terms of communication, localization, or sensing. So the question is, how are these spatial processing modes related to the 3 connectivity types I was describing for 5G? Let's take massive MIMO and IoT. The pros of using massive MIMO are that we have a lot of antennas, so we can in principle get very high signal to noise ratio because we can collect energy from many antennas coherently, hopefully. Then the law of large numbers makes that these links are quasi-deterministic, so they have immunity to fading, and they can have a very predictable SNR. And then, of course, there could be many devices transmitting simultaneously, and they can still be resolved even in the same spectrum because there is an extreme spatial multiplexing capability. The problem here is that massive MIMO has all these advantages, provided that it can acquire elaborate channel state information. So there is a procedure to gather this channel state information, which in terms of protocol is just additional protocol steps. So if we were looking into the reliability problem, that means that we just have even more steps in the whole puzzle of reliability. So to guarantee 10 to the minus 5, that means that each of these protocol steps should work with, let's say, 10 to the minus 7, right? Then that's why we have to look into modified way how to use massive MIMO and IoT. And here is an example of a factory scenario where we have a massive MIMO access point. And then this is a quasi-static environment where the devices have discovered multiple spatial channels towards massive MIMO, so they can actually pre-code the transmission without having a need to learn the channel every time in order to reach this massive MIMO through some predefined spatial paths. And if you want to add the reflective intelligent surface, then this reflective intelligent surface can try to make sure that these spatial channels, which are known by the devices in the factory, they're kept more or less constant. Another example of using a configurable intelligent surface for IoT devices is that we have relatively weak IoT devices with weak transmission power. So in principle, this RIS acts as a booster of their signals to actually direct their signal to the base station. And a scenario where we have looked into this quite concretely is a scenario of a satellite IoT, which is another popular area. So we have a reflective intelligent surface deployed on the ground and close their deployed IoT devices. And these devices, they can actually transmit to the satellite. But besides the direct path, there is also a path which is going to the reflective intelligent surface, reconfigurable intelligent surface. There are different names for this acronym. And then the thing is that because the phases and the reflection coefficients can be changed in this, and let's say that the movement of the satellite is predictable, then in principle, this setup can be used to decrease the Doppler effect, to control the Doppler effect, to control the time spreading of a signal, or to maximize the SNR. So, so this is an example how a predictive mobility in the case of satellite communication could be used to boost the uplink communication of low power IoT devices. And actually, IoT devices and satellites is a new trend. There's a trend to use the terrestrial IoT technologies like LoRa, Sigfox, NB-IoT to be transferred to satellites, and there are actually companies doing this. And generalization of this is something we are working currently on, is to how to have multiple of these reconfigurable surfaces which are shared by many devices. So this is leading to new types of multiple access problems, where instead of only looking into how to resolve the collisions and how to process the signals at the destination, we actually have to see in which way we should reconfigure the intermediate reflector, which is here the RIS, in order to help multiple IoT devices at the same time to reach the satellite. Final part is about blockchains and distributed ledgers and IoT. So when massive IoT systems were designed, so when this standard started to come out, like Sigfox, LoRa, and NB-IoT, the interactions in massive IoT systems were envisioned to be mostly uplink. So there are mostly uplink transmissions. There is, for example, a sensor in a garbage can. There is a sensor of CO2 and a similar thing, which is occasionally transmitting data sporadically. And that's the model of what was called before mMTC. The thing is that there are at least two drivers to change this pattern of interaction. One is the smart contracts and blockchains, which I'm going to speak about. And the other is distributed learning. So in distributed learning, what I mean is that the devices might not only report data to the network, but actually they might be contributing to some form of, let's say, I don't know, distributed learning, federated learning, or the other fashionable learning forms, where they can try to learn certain model of the application that they're supporting, but with the help of the network. And in that case, it cannot be based only on uplink transmission. We have to transmit learning related information back and forth to these devices. So from the communication viewpoint, this is important because this is changing the basic assumption of the IoT traffic. In principle, Sigfox and LoRa, they are not really intended to handle symmetric traffic, but NB-IoT, on the contrary, is capable to a larger measure to actually deal with symmetric traffic. So what is a distributed ledger and why it is important for IoT? So distributed ledger is related to blockchains, and blockchains are related to Bitcoin. And ideally, it's a truthful, immutable account of the history of transactions among networked participants. Actual one, and I guess many of you know this, is that this approximation of this ideal or distributed ledger, where we have non-zero delay and non-zero probability of error for writing in certain databases. So we have to have actually a very non-trivial consensus among the nodes to agree what has happened, and that has happened to be written in the distributed ledger. And it started for financial transactions. For example, if I transfer some money to somebody else, which is part of the network, then his account should increase for that amount of money, let's say $10, and my account should decrease for $10. And then everybody has to have a consensus about this. But actually, it can be generalized. It can be made into, then there's another way which you can use the distributed ledgers and blockchains is to run smart contracts. So smart contracts is about being capable to modify the state of a database through certain predefined set of functions. For example, if you are doing pollution monitoring, then the point is that once you have a value of the pollution, you want to agree on that value with the others that are measuring pollution, and then you don't want that this value is changed afterwards. This has nothing to do with finance, but it has to do with trust and immutability of the account. And blockchain is a very specific instance of a distributed ledger that has a linear chain structure, but it's one of the most widespread within the last decade. But there are other structures, like IOTA has a directed acyclic graph. And the objective is to have these finalized transactions. These are transactions which are accepted by the participants in the network. And smart contract, this is an example of a smart contract, for example, for renting a bike, where a person, the smart contract is kind of witnessing the terms by which a certain person is renting a bike. Then the point is that when we start to have many IoT devices interact with each other, basically agreeing on what was the measurement of certain parameter, or trying actually to sell and buy data to each other in an autonomous way, then we need to have certain mechanism to ensure trust. And this mechanism, a good candidate for this mechanism is a distributed ledger. Then some of you might ask why somebody from the wireless communication and specifically communication theory cares about this. Well, you are in California where there was a gold rush almost 200 years ago. And the people that really earned money in that period were the ones making the shovels. So in that sense, for communication viewpoint, regardless of what the application of blockchain will be, there will be a lot of communication. So we'd better prepare to the systems to be able to deal with this communication. How can we fit distributed ledgers to what I talked before, massive machine type communication and URLLC? Because these are two, let's say, different types of IoT services. One is a massive IoT service, the other is ultra reliable. The challenge in massive machine type communication is the other computational requirements and the protocol overhead, because these devices, as I said, LoRa, Sigfox, NB-IoT, they are not intended to handle the heavy computations and heavy communication traffic from a blockchain. The challenge in URLLC is different, because in URLLC you look at the low latency, and now when we have a consensus, the question is, should we measure the latency of 1 milliseconds or 10 milliseconds of a transmission, or should we measure the time until consensus has been reached within the network? And this is yet another generalization of the timing that I talked before about. So we have actually made a case study in how distributed ledgers are fitting some of the IoT technologies, and we have actually tried different distributed ledgers: Ethereum, IOTA, Bitcoin, Hyperledger Fabric, and we tried to see what is their latency in LoRa, which is a widespread IoT technology. And the results were not promising. For example, we saw that in the case of Hyperledger Fabric, we had latencies of for consensus which were above 80 minutes, 100 minutes. And the reason for this is that the transactions, the way transactions are done in this specific blockchain, they are not meshed to the, let's say, duty cycling in the activity of the links in LoRa in this specific system. So I'm not saying that this cannot be optimized. I'm just saying that trying to fit these two systems without specific optimization might lead to results which are not really promising in terms of latency. Another application we are working on is the pollution monitoring with IoT and blockchain, which I mentioned before, where we are actually trying to have a trusted ledger, trusted account of what happened with certain measures that were taken of CO2 or NOx and so on. This is the practical setup that we have. Why is this important? Because with all the green quotas which are coming now, CO2 quotas and pollution that can be made by cars and by other entities, then we would like to have a trusted mechanism to record everything that is happening with respect to the pollution so that they can be taxed afterwards properly, right? And this is distributed ledger is a candidate to do this. Another thing we are working on are distributed markets, where we are allowing the devices to IoT devices to trade data among themselves. So it's basically decentralized trading for IoT systems. And again, what our interest was here is to design generic types of markets and see what are the communication needs. And the important message here is that if you have IoT devices which have intended lifetime of, let's say, 5 to 10 years, once they start to participate in this kind of trading processes, their lifetime decreases significantly. So it's really important to choose the markets which are most efficient in terms of energy efficiency. So this brings me to the end of my talk. It's exactly 45 minutes. So it's what I talked was the connectivity landscape and the challenges in understanding the interaction among different generic types of services and traffic. Then I have the hypothesis that the spectrum usage will be redefined by heterogeneity, and it will be exciting to see what will be the methods for slicing of the spectrum that are going to be developed, both in terms of technical solution, but also regulatory. Then we are starting to have better understanding of the timing requirements with respect to different cyber physical systems where wireless connectivity is used. There are new opportunities in spatial processing, not least in the area of reconfigurable intelligent surfaces and impact on the wireless environment. And finally, I have also shown that distributed ledgers can support autonomous interactions among IoT devices, but they're fundamentally changing the interactions and the traffic patterns in these systems. So thank you very much for your attention, and I'm open for questions.
Right, thank you very much, Peter, for the great talk and the amazing system level perspective that you have also opened up. And it's interesting to see how indeed the change in all the layers that cyber physical systems are incurring are impacting fundamentally even the notion of times that we usually have with computing systems like latency and throughput and so on. And all right, and I open the stage to questions. So everyone is invited. I mean, if we want to ask a question directly, you're very welcome to raise your hand. Otherwise, we will be happy to take questions from the Q&A or the chat. So feel free to ask. Might be actually starting just with the new notion of times that are emerging in your exploration and so on. And in particular, this aging so it looks like, or this fact that indeed you are checking, for instance, when there is actually a change in the system dynamics in order to evaluate whether the information is old or not. So do you then need there indeed some assumptions, right, on the dynamics of the system, or are you expecting that the control layer would, or cyber physical system would give you time constants, and does this cost or not? And what if in a federated learning, for instance, approach, you don't know that, you have to learn them and so on?
Yes, so yes, that's the point for defining this notion of time was actually to try to understand how the end users in cyber physical system, and especially, for example, the control or learning that they're going to deal with it. So you can think in the following way. Let's say that you have a controller which is getting data from remotely. Then the controller might be a Bayesian system, which is basically just updating the belief every time a packet comes. The question is, if this packet doesn't come, what will be your action as a control system? And the interesting thing is that we are working with Bosch, actually, with the PhD student on a wireless control of this automatic vehicle. And the interesting thing is that if you take the traditional criterion that if 3 packets are lost, the whole system gets shut down, is actually not correct, because if you have some machine learning model at the controller that is building up what is actually happening at the size of the AGV, then you can say, okay, I have not received the packet, but based on the previous situation I have seen here, this is not a dangerous situation. So even if I don't receive 5 packets, it's fine. But in other situation, if your belief is different, then even after a single packet not received, you say, okay, this situation is dangerous. So there is really an interaction between the model that you're building for the remote system, that's a learning parameter, and then what is the performance of the communication. And then the notion of time, to be very honest, I'm very confused with this, because once you start to think about it, it starts to be very crazy. Like what is a simultaneous? What does it mean simultaneously? You even can say that when the transmitter perceives certain time, until the transmitter knows how the receiver perceives this time, the minimum time that should pass is the round trip, right? Because the packet should come back, and then so this is the minimum time resolution by which the system can work. And then the question is, if this time resolution is more than what your control loop is allowing, then you probably have to work with unacknowledged transmissions and so on. So I think it's really interesting.
Absolutely. In fact, indeed, it's challenging also for people in control, indeed, to propagate sometimes, right? We look at the other perspective, like communications constraints, but now actually there is another avenue here in which, that's very intriguing. All right, so actually questions are coming up on both the Q&A and the chat. So on the chat is, so where do you see the role of AI actually in blockchain out network?
So this is a difficult one, but I can tell for one question where I believe that that is important is let's say that the blockchain can be used in the distributed learning models to verify the authenticity of the data which is being used by this learning, so to prevent data pollution. And for example, in federated learning, I've also seen works where we are using blockchain in order to be able to track who has provided data which was fake and then was ruining the learning process. But that's the first. And the second one, which I think is paradigmatically important, is that these distributed ledgers and payments are going to be important if you would like to trade off your privacy for the payment of for the data that you are getting. So currently, we're getting all these free services for the companies where we're providing our data unconditionally. But in principle, if you have a distributed ledger, you can actually decide how much of your data you want to sell and what will be the price of that. So you're kind of, the way you are feeding the learning process, you're controlling the price of the data that you are providing there, and you're controlling how much about yourself you're revealing. And this is one role where blockchains can be used to underlie distributed learning process. And I guess there are other applications about I'm not expert in AI or in blockchain by itself, but just telling about applications which I have seen are emerging with respect to, let's say, IoT devices and communication.
Right. From the Q&A, what do you think IoT technologies like LoRaWA will converge with 5G, or would you think so? Sorry, or will the two technologies diverge for different use cases?
Yeah, I think the winner on the long run will be the one that is going to integrate all interfaces, regardless of whether they're coming from 3GPP or not. Because everybody speaks about 5G, but I'm almost sure that 99% of us which are connected to this Zoom talk are currently using Wi-Fi. So, and Wi-Fi is not going to disappear. On the contrary, and LoRa, it has its strength in terms of robustness, the long range, and so on. And it might be supplementing the 5G services. So 5G, I don't think that 5G is going to be to wipe the wireless table and then nothing else will. Although people were thinking about this already with 4G, with femtocells. I mean, how many of us are using femtocells now? I guess all of us are maybe using Wi-Fi at the moment. So I think the same thing will happen there, that LoRa, Sigfox, they have their markets and they have their sectors where they're performing well. But I try also to say that if we have asymmetric traffic, application with symmetric traffic, then maybe they're not the best choice, but not every traffic will be symmetric. It's just another development.
Mm-hmm. One question, in the presentation, there was a slide about different traffic patterns in a massive IoT network and IoT sharing learning data. Would that be a high risk to cybersecurity?
I mean, of course, it would be, because here the cybersecurity attack could be just to basically inject false data that it disables you to learn the correlation in the traffic, and then when you allocate the traffic, this is not going to work, and this is a cybersecurity threat, right? But if I understand the question correctly, is that this learning, the learning, that what I meant here is that this is the traffic which is coming from the same device. So you have a device connected to virtual reality, and then there is a tactile input, there's a video input, and so on. So we try to understand the correlations within that device. But you are right that if we want to optimize the spectrum usage and try to understand the correlations across different devices, then in principle, there is a cybersecurity threat there, because we could have devices which are cheating in this process of learning the correlations, and then when the actual allocation of resources happens, it's not corresponding to reality. So basically, we are not capable to meet these service level agreements. And my favorite example of that is the ultra reliable low latency, because what I think I mentioned in my talk, but I didn't talk about that a lot. When I come to Bhaskar and I say, I'm going to sell you an ultra reliable system with 10 to the -5, how can I convince him? We have to actually run 10 to the 10 samples until he's convinced. So we have to have another system, right? Another way in which I can sell these systems. And it's interesting that this is not well understood. And we actually started to do a framework on this based on statistical learning, but I think we are far from understanding it well.
So, so do you believe, just actually there is another question also on the cybersecurity follow-up, but just to, yeah, I was chiming in. So do you believe that wherever testing, cannot help enough, some kind of formal analysis might be helpful there?
Yes, I think the formal analysis is in principle machine learning, which happens over different generation of people, right? Because that's how we learn the model, and we are trying to set up this model. So that's kind of a knowledge from a longer period. I think the way you're right. When we have a lack of testing data, there are two things we can do. One is the formal model, and the second is a Bayesian approach with certain priors, where you're building certain prior. Another form we are trying to use at the moment is to use some form of meta learning, where you're trying to guarantee reliability in some environment based on what somebody has learned in another environment, and then I can try to assure you that in your factory I can give you 10 to the -5, provided what I did in the factories in Denmark, for example.
I see. So some kind of principal transfer of the knowledge from one system to
exactly.
Yeah.
Exactly.
So continuing on the cybersecurity question, aside from trading privacy for better service, is it possible for a hacker to use the blockchain to dump trash data onto the network and manipulate the learning model? Yeah,
I think Bhaskar is far better expert than me in cybersecurity. So if I can try to cautiously tell here what I think about this. But blockchain is a garbage in, garbage out system. If you put data which is not correct, you're not going to get something which is correct. So we should not think that the blockchain is preventing misbehaving. In the same way, the criminal law is not preventing misbehaving. You can still misbehave, but then you will be punished afterwards. So blockchain is just ensuring this immutable, that if something happens, you can go back and trace it. And this is in principle not a preventive role. So yes, it can happen to have a trash data, but the way we have to prevent this is probably with certain other high level, logic of the system in the learning process, and checks in the learning process and so on. But not, I think the blockchain by itself doesn't know what is the correct data.
Yep. What are the risks associated with blockchain processing? Is there a risk of data loss as well? Thank you in advance.
Yeah. So if you talk to the people that work with blockchain technology, really cryptographers, that they make these beautiful proofs about the consensus and convergence and so on. The trouble is that these proofs do not work if the wireless links are off. If simply you disconnect the device, then it's not part of any consensus. So so in principle, these systems are vulnerable to the lack of connectivity. And associated the risk that could be associated with blockchain processing in terms of IoT devices is that the IoT device cannot be, or it's difficult for the IoT device to be a full member of a blockchain network, do all the processing, participate in the consensus and so on. So very often it will just give part of this role to certain device which is at the edge. So in principle, if this device at the edge is compromised, then we have a problem with the trust to the IoT device which is connected to it.
There are just a couple of further follow-up, but mostly a thank you on the cybersecurity question before, and on the chat one last. So are there threats to biodiversity when scaling wireless devices across different spectrums as well?
Yes. Yeah. So this is a controversial question, controversial topic, not the question. The question is fine. This is a controversial topic because so far, again, I'm not an expert in wireless radiation of the health the health effects of a wireless systems, but there are people that are experts and they're constantly evaluating this. And in principle, our role as communication engineers is to respect the safe bounds that they're putting. Right. The more we understand, the lower this bound should be, or we can better meet these bounds and so on. So the truth is that we don't know the long-term effects of any technology. We don't know now there's talk about this mRNA vaccines and what will be the effect. Okay, we know based on the statistical tests now, but we maybe do not know some effects that will come over a longer time. But based on what we are seeing currently for the wireless towards millimeter wave, there is no harm to humans. But I think the technologies like reconfigurable intelligent surfaces, and actually we just today had a kickoff on a European project on that. I believe we should not just beam wireless signals to the users, to the humans, and to the living things. Basically, we should try to recycle the wireless signals, recycle the wireless waves, and try to direct them where they are needed. So in principle, at the moment, through myself and through yourself, there's a lot of wireless signals which you are not using and they're passing through you. The point is that if you have this control of the propagation environment, maybe these signals will decrease, and in principle, it will less affect the environment than what is happening now. Keep in mind that the biggest threat comes from the mobile phone when you're talking. When you were talking on a 2G phone, you are much most exposed to radiation compared to having Wi-Fi surfing on your iPad in your hands, right? So let's not forget about this.
One more on the question and Q&A. So 4G and Wi-Fi have a problem with the service stability and security. New technologies like 5G have always problems with connection stability and reliability. How does 5G technology develop the stability and reliability rather than 4G and Wi-Fi?
Yeah, so the point is that where 5G is going to need a very high stability and reliability is, let's say, private networks. So industrial networks where we would like not to rely on public Wi-Fi. We don't want to rely on 4G. That's why there are these private 5G networks where first of all, we want to allocate spectrum, which is licensed and locally used in certain factory. So the way, so that's the first level of ensuring that there will be less interference. So you're not going to share with other Wi-Fi devices or with other 4G services. The second is the paradigm of slicing. So in network slicing, there have been a lot of work in higher layers about how to ensure that the computational memory resources and connectivity resources are allocated in a way to meet certain reliability requirements. And ultimately, the role to meet these reliability requirements will be coupled with a certain use of machine learning, because we have to have a machine learning model that is assessing what is the current state of the connection, whether it should allocate more spectrum, more computing power, and so on. So in principle, we need to constantly monitor the statistical quality of a connection, and 5G has the capability to allocate flexibly resources because it has this very flexible way of expanding the resources and allocating resources to a given connection.
Right. So it seems that, yeah, most of the questions have been answered, and there are others still welcome.
Yeah, they're also welcome to drop me an email. It's on my emails on my slides. So
yeah, absolutely. And yeah, we are kind of about the time also. All right, so thank you very much, Peter, for the great insightful talk and exchange after as well. And to everyone, I'll see you all then next week at 2 p.m. this time for the...
Thank you very much for the invitation. It was great talking to you. Thank you.
Yeah, and as I usually say, we hope that in a new normal situation, we are able actually to invite our speakers in person as well.
We'll be happy to do so. We'll be happy to do so. Thank you very much.
Thank you.
Thank you.
See you, everyone.
Bye.
Bye.
Bye.